Good afternoon. I've had all the good afternoons rolling in the chat. Nice to, nice Tuesday out there. Okay, so confession time. Remember how we had those, or I had those internet issues with my video. So of course my video is all chopped up. So I'm gonna try to kind of force them all together, but I kind of had a weird weekend, so I didn't have time to sit down and do it over the weekend. Not weird, we just had a lot of visitors and stuff like that. So I'll put it together as best as I can. One doesn't have any video, so that one's kind of useless. So I'll cut that one. Yeah, just what a mess. But anyways, I'll try my best to get some sort of video out there, but you have the notes, so that will be good too. Okay, so last day we wrapped up chapter 5, which was on classification, right? So we were talking about classifying categorical variables, right, as either a success or a failure. We can extend it to multiple categorical variables, but we focused on binary variables because we also know that we can usually turn a categorical variable into a binary variable, right? I feel like there was another thing that I wanted to say to you guys. Oh, it was just a random thing. Let's see if I can find it. Have I shown you guys the website Spurious Correlation? I think it's Spurious Correlation. So it pops up here, and I can't remember if I showed it to you guys in Stat 230 or not. But anyways, it's a really fun website. I mean, oh, I haven't shown you. Okay, so let's see if I can copy this and potentially paste it there. Anyways, it's just a really fun site where, and a lot of it is morbid, but you know, whatever sells, right? He's not selling anything, but let's see here. He's found all these weird correlations. So the correlations are quite strong. This doesn't really have anything to do with what we're talking about today, but I realized the other night that I haven't shown it to you guys yet. So here we go. So what I wanted to, I want to zoom in just a little bit more. So for example, the number of people who drowned by falling into a pool correlates with the number of films that Nicolas Cage appeared in, right? And so for each year, right, Nicolas Cage would have been in some number of movies, and there would have been some number of drownings by falling into a pool, for example. Right. And so the correlation here is really strong. We know that they're not related, right? They might be correlated, but we know that they're not related. That makes no sense, right? But this is something that's really good to keep in mind, right? If we're talking about correlations at some point, then we have to understand that unless we know that it makes sense for things to be correlated, we can find correlations between things that are not related, right? And so so that one's kind of fun. The per capita cheese consumption, so how much cheese is consumed, correlates with the number of people who died by becoming tangled in their bed sheets. And so that's quite high, the number of people. So he gives the correlations 94.71. Let's see if I can screenshot this. Oh, it's so loud. Oh, the chicken consumption. I'll go to that one. I'll save this one first. But if I scroll down, let's see here. Oh yeah, the age of Miss America correlates with the murders by steam, hot vapors, and hot objects. Arcades, space launches, mozzarella cheese, fishing boats. Oh, that one's kind of, haha, here. You get a correlation of 89.99%. So imports of oil and per capita consumption of chicken, I don't know, but they're definitely correlated, right? So no, there's no causal relationship. In fact, you can't really talk about causal relationships until you've done an experiment or something that's really, really structured, right? So causal relationships, you kind of want to avoid talking about causal relationships because there are things like this, right, that could be going on. And so you don't want to say that the consumption of chicken causes an increase in the US crude oil imports. Although this one, to me, I can kind of get there, right, if I think about it. Okay, so yeah, right, like how much, if we're eating more chicken, then we need to drive the chicken and maybe we need to import the gas, right? So I can kind of see this one, but there's not that direct correlation, of course, that we think that we're seeing here. Let's see if I can find, there were some other funny ones. I mean, oh yeah, this one, the letters in the winning word of the spelling bee correlates with the number of people killed by venomous spiders. So should we have, so the correlation is positive, right? 80.57%. That means that we should have short spelling bee words to avoid people being killed by venomous spiders. No. Hey, I've never looked at this one. Math doctorates awarded, uranium stored at US nuclear power plants. Anyways, so just kind of a fun website to check out and just something to keep in mind, right? And so I was thinking about that. I was like, oh, I don't think I showed them this yet. It's one that I like to pull out every now and then. All right, so maybe I'll say that this is totally random, but check out spurious correlations for fun examples of things that are correlated. For fun examples of things that are correlated. I'll put a little, crop this up. So it's just kind of a fun thing. All right. And I think the website is tylervision.com, and he's the one who's done this. I'm sure he gets lots of traffic. I don't know. But anyways, it's kind of fun. Okay, so I'm curious, how many of you are taking or have taken machine learning already? I think it's with Bevan, right? Okay. Yeah, so I think a lot of you are taking it. Maybe not have taken it yet. Right? So chapter 6, forgot what chapter it was, is on machine learning. We are just going to touch the surface, right? So it's going to be one of those nice chapters where if you've taken machine learning or you are taking it right now, then we're just going to do a quick review. Question? Or was that like a yes, I have? Hand up. Oh, nice. Yeah, so then no, don't ask me. I don't have a question. No. That was always me in class. Remember when you had to go to class, right? And sit in class? I would always just be writing head down, like, no, don't ask me, please don't ask me. Yeah. Yeah, don't worry. Even when I do have classes in person, I don't ask people questions specifically. I think it's really mean, because my heart would just go, ah. Anyways. So anyways, it's just me maybe. Okay. Oh yeah, so chapter 6 is on machine learning, and we're just going to kind of touch the surface, and you'll either see more with Bevan or you will have seen more with Bevan, but it's just going to give you some of the tools that you'll need. Remember, we're just kind of doing a broad overview of everything, so a little bit tricky, but okay. So we'll start, and we're going to talk about things like k nearest neighbors. Now, especially when I was kind of getting into this stuff, I found it really confusing because sometimes we use k nearest neighbors as a way of predicting things, and sometimes we use those k nearest neighbors as what we call a feature engine, so as a predictor in our model. And so we're going to kind of tease those apart, although they're definitely related. We do the same thing, but then we incorporate it as a predictor. But there are kind of two main things that we could use k nearest neighbors for. Okay, so chapter 6 is on statistical machine learning. Right, and so machine learning, we're just scratching the surface here. You will see way more with Bevan. So you will see or have seen more with Bevan. I think it's Bevan that teaches it. Okay, cool. Thank you. So, right, so, but what's nice is the textbook includes some core kind of code chunks that you might want to have up your sleeve, right? So this book introduces you to kind of the basics of everything that you might need in data science. And then of course you can do more research and kind of build on this, okay? And so the first concept that we're going to talk about is k nearest neighbors. Okay. And k nearest neighbors, we can use it we can use, and I'm going to write KNN because that's what it is, K nearest neighbors, which is different from K means, right? But although it's similar, right? Which we haven't talked about yet, I don't think. I'm trying to remember. I don't think so. But we can use KNN in kind of two capacities. In two capacities. So the first one is for classification or prediction, right? Classification is for categorical data and prediction is for numerical data, right? That's the only difference. Okay. And so for classification or prediction, and classification, right? Let's just emphasize is for categorical data, or prediction is for numerical data, right? If I'm trying to predict a numerical outcome, in fact, I'm going to say categorical outcome instead of data because it's just the outcome that we're talking about versus a numerical outcome. So we can either use it for predicting an outcome, right, or classifying an outcome, and we'll elaborate how we do it. But I think you have seen it at some point, maybe not in action, but in theory, right? And so the second way that we can use it is to incorporate some of those key variables, right? And we can use this, the classification or the prediction, right? So the second one would build on, okay, you make a prediction or you do a classification, and then we use that as a feature to model our outcome, right? And so then we would use, maybe if we're doing a classification, right, I would include the probability of it being class 1, and then I would try to maybe use a logistic regression to classify the outcomes. So then I incorporate those nearest features, right? So those nearest neighbors, right? I incorporate that, okay, this is how I predict this thing will behave, and then I use that in my final model. Okay, so for classification or prediction, or as a feature engine. Now, a feature engine, we generate, or rather we use the classification or the prediction from 1, right, as a predictor in our classification or our regression model. So we use the classification or prediction from 1 as a predictor in our classification or regression model, which is a prediction model. Classification model, right? For example, maybe a logistic regression. Right, as a predictor in our classification model or prediction model. For example, a linear regression. Right, so we can use that prediction as one of the predictors in our model, right? Because it's saying it's basically incorporating just those nearest neighbors, right? And so it's not looking at the entire data, it's just looking at, okay, how do the nearest neighbors behave? Then I factor that in. And a really good example that the textbook uses is if you're working with a realtor or a real estate agent, for example, then their job, I guess, is to give you a fair price for a property, right? So how much should you be offering? What is this property going to be worth? What's it going to sell for, right? They're predicting the sale price essentially, right? And so so then they would look at how many bedrooms are there, how many bathrooms, where is it located, right? They would look at all those different variables. But another variable that they would have to consider is what did similar listings sell for, right? So you don't look at the average sale price in Kelowna. I think, well, we shouldn't talk about the average because prices are typically skewed, but we still do, right? And so just keep that in mind. But we still talk about the average sale price, but we should also look at the median sale price, right? Because that's the 50% cutoff, right? Back to 230 here, right? And so, but if we talk about the average sale price in general, right, that doesn't tell you anything about your specific property. So then you focus on, okay, well, the average sale price for these types of properties, right, then that gives you a better idea of what the predicted sale price would be for that specific property, right? So you narrow it in on those nearest neighbors, right? Ironically, potentially also physically nearest neighbors, but in terms of the predictor variables, the nearest neighbors, right? So really good intuitive example to think about, right? So good. So that's how we would use the k nearest neighbors as a feature engine, right? Remember, a feature is a predictor, right? So it's an explanatory variable, right? We haven't called it explanatory variables in a long time now, right? But those features and predictors, they are just explanatory variables. And so here I'm going to say recall the explanatory variables are predictors, which are features. We can go on, the list goes on, right? Depending on what field you're in, you're going to use different terminology. So for data science, we use features and predictors most of the time, right? But when we're first introducing things, we use explanatory variables, right? And that's just to emphasize that it's the X, right? The X. Okay. So what do we do to run a k nearest neighbors in theory, right? And of course, there are built-in functions in R, especially, and I'm sure in Python. I've kind of been skipping the Python code. It's nice to have it there because then we can kind of learn by doing. But I've kind of gotten lazy and skipped through it. But let me see here. There sure is Python code in here. K-neighbors class. Okay, and so there is a k nearest neighbor function in R, but what they recommend is that the fast nearest neighbors is going to be better, and it's going to extend to larger data sets. So just kind of play around with those, and they do the same thing. It's just how they do the algorithm, I think. Okay, but so in general, k nearest neighbors, we have a set of predictor variables that we want to find a classification or a prediction for, right? So given a set of predictor values, we want to classify or predict the outcome. we want to classify or predict the outcome. So what we're going to do is we're going to have our data set, right? And so each of these predictors are going to have different values, right? And so we can find all the two bed, two bath apartments that are downtown and maybe in a specific area, more specific than downtown, maybe built between the time or later than the year 2000 or whatever kind of filters you want to put on there, right? So you have some predictor variables or values that you want to predict the sales price for example, right? And so then what we do, our k-nearest neighbors is going to go through our entire data set and it's going to pull out, right, those nearest neighbors, those set of predictors that are closest to the set that we're interested in, right? And so we search the data set, and we do not do this, right? But in general, right, what's happening in the algorithm is we search the data set for the observations with the closest predictor variables or the predictor values that we're interested in. For the observations with predictor values closest to the predictor values of interest. Predictor values of interest. Okay. That kind of opens up another can of worms, right? How do I define the closest, right? And so we have to think about this. We're going to parking lot that for just a little bit longer, right? But that is something that we're going to need to tackle. Okay, well, how do I determine what's close, right? And we probably remember that you have these different distance measurements, right, that we can use. But in general, the Euclidean distance is the one that we're going to use, right? And so I'll parking lot that until later, but notice, right, we hit the snag of, okay, well, how close is close and how do I measure that closest distance? Okay. And then for classification, right, you can look at the majority of the outcomes, right? So if it's a binary outcome, you can look at the majority, is the majority 1 or is the majority of 0, right? And then you would give it that classification, right? The majority determines the classification. Determines the classification. So what I mean by that, for example, 60 out of 75 are 1, then the classification is 1. Right, so the majority rules, and if you have 60 out of 70 zeros, then the classification would be 0, of course, right? That's one of the ways that you could do this, right? You don't have to take the majority rules, but that's the most common thing that you're going to do. Whereas for prediction, right? Now you don't have counts in each category, right? You're going to have some numerical outcome. Which method? Sorry, I think you'll need to clarify. I don't know. About, for classification, usually we use the majority. So that's going to be your default. This textbook doesn't even introduce anything else. But I know that there are others out there, but don't let that bog you down, right? So the majority, and maybe what I'll do is here, I'll make a side note here. Other methods exist, right? But this is the one that you're going to use, right? But this is most popular, right? And it will serve you in any scenario, right? Because even if you have to, support your findings to your boss, then that's an easy sell, right? Why did you classify this as a 1? Well, because the majority of the others that looked like this were a 1, right? And so that's an easy sell. And so that's what you have to think about as well, right? When you're adopting these different techniques, you're going to have to explain yourself to people who don't know what you're doing, right? And so, yeah, so for classification, you're going to go with the majority. Yeah. Right. And so you always want to think about, okay, I could do these fancy things, but will I be able to explain what I did to my boss, right? Or will I be able to convince some stakeholders that what I did makes sense, right? And so you always want to kind of pick the simplest route that does what you need it to do. That doesn't mean that you shouldn't consider more developed, more advanced techniques, but usually you're going to end up going for the simplest technique just for the sake of having to explain it later, right? You don't want to have to explain and give a whole, a whole lecture on why you did what you did when it could be as easy as choosing the majority, right? So that's why we're going to go with the majority. Nice. And then for the prediction, typically we just take the average, or, it could be the median if you have some reason to select the median, right? But so for a prediction, now we have numerical outcomes. So numerical outcomes mean that we have to take the mean. Oops. The mean, right, or other measure. So again, you could use something else, right? Or the median, or I guess you could talk about the mode if you wanted to, but that would be weird. What's the mode? It's just the most frequently occurring value. It's more for categorical data actually than numerical data. But I guess you could get weird with it. But again, the mean, and I'm going to underline it here with orange again, because this applies again. And maybe what I'll do is I'll delete that because it's the same explanation, right? So for prediction, the mean outcome will be the predicted outcome. The mean outcome will be the predicted outcome. Okay, so here, right, I just want to make a note of what we were just talking about, right? And so in life later on, you'll need to explain what you did. So you will often need to explain how you arrived at these findings, right? And you often need to explain it to people who don't know this stuff. They've paid you to do it because they don't know how to do it, or they don't want to do it, or both, right? Usually it's both. But they don't want to say that. And so they just say, oh, I don't want to do it. But maybe they just don't feel comfortable doing it, right? And so it's good to hand it off to someone who does. So you'll often need to explain, right? Explain your methodology. Your methodology is just how you solved the problem. Okay, so in general, okay, so what I did was I used k nearest neighbors. And what that does is it looks at the predictors that are similar, and then I assigned it to the majority vote, right? That would be your methodology in a classification case. Okay, and so you'll often need to explain your methodology to your boss or stakeholders. So usually we opt for the method that is the easiest to explain. So usually it is beneficial to opt for the method that requires the least amount of explaining. That requires the least amount of explaining. Okay. Again, that doesn't mean that you shouldn't consider those more advanced techniques if you have them and you're ready to use them and you know that they're appropriate, right? But just remember, you have to explain them too. So that requires the least amount of explaining, unless more advanced methods are, I want to say much better. That's not what I want to write down, though. That's not proper English. So the least amount of explaining, unless more, I wanted to say expensive, more advanced methods yield significantly better results. Yield significantly better results. Significantly, it could be as sophisticated as, you know, a p-value less than 0.05, right? That's how we test significance, and that's how we deliver significance. But it would be hard to compare values, maybe. Okay, but in general, just if you have a significantly better result or a predictor or a classification model, then of course you would use that. You're not gonna toss it just so you can explain what you did, but just remember, you always have to explain what you did. Okay, so K nearest neighbors considers the predictors that are the closest, right? And the K is the number of neighbors that you consider, right? And so K and N considers the k, and I'm going to say closest, and I highlight it again, closest neighbors right? And so K can be some number, but let's talk about, you know, the differences between the different Ks. And there are methods to figuring out what the best value for K is, right? There's that elbow graph that you could do, but let's just ignore that for now. And let's focus on the closest, right? How do we determine the closest neighbor? And I guess I should closest is measured by a distance metric. Is measured by a distance metric. Okay. Now, for us, the default is going to be the Euclidean distance, and that's going to serve us well. You know, if you just want to have this one distance metric, then that's fine. There are lots of other distance metrics that we could talk about. And I know in Data Science 300, we talk about a couple of more distance metrics, but then we say, oh, our default is going to be the Euclidean distance. And so let's just focus on that one, but I'll also talk about the Manhattan distance. So the closest is measured by a distance metric, and the default is the Euclidean distance. Okay, the Euclidean distance is that the distance kind of as the crow flies. Okay, and so if you have some point A and some point B, how would you find that distance between the two? You have a couple of options, right? But the most obvious is going to be this distance. That is the Euclidean distance. And oh, it's not IA, it's EA, sorry. I started thinking about, okay, well, it's Euclid, so Euclidean. Sorry about that. Okay, so the Euclidean distance is like that. Just as you would probably have found the distance between A and B. Now, what do you have to do? Well, you'd have to take, right, A squared plus B squared equals C squared. All right, so you could take this distance and this distance. So if this is A and this is B and this is C, right, then A squared plus B squared equals C squared. So C is the square root of A squared plus B squared. We're going to do an extension of that, but now I don't just have 2 points. I have multiple predictors and I have these vectors. And so the Euclidean distance is going to be x1 minus u1 squared. So the distance between x1 and u1, and then plus x2 minus u2 squared, all the way up to the number of predictors xp minus up squared, and then we take the square root of that. Okay. So that Euclidean distance is some square root, and of course our Python has it built in. And so that the default distance metric is going to be the Euclidean distance. What's another distance that we could have measured? Well, we could also consider the Manhattan distance. Manhattan distance gets its name because you're thinking about city blocks, right? And so if you're going from A to B, but now you have blocks in the way that you need to follow, right? You're walking on the sidewalk, then there is only really one way, or I guess two ways that you could go, right? You could go this way and then this way, right? Or you could go right this way and then this way. Either way, that's the same distance, right? And so that's the Manhattan distance, which is going to be the absolute value of these guys. And so, but I'm not going to write that down, right? So imagine that you're traversing city blocks instead. So then you can't cut across these buildings because that would be weird. So then you have to go around the block. Okay? But those are some of the distances that we could talk about. Okay? But we're going to focus on, so the default is the Euclidean distance. Okay? So that's how we determine how close everything is. Okay, so if I give you some predictor values, okay, so give me a classification for, or maybe give me a predicted sale price for an apartment, and it is 3-bedroom with 2 baths, right? And it has a view of the lake. Uh-oh, sale price just went up, right? And so all these things that we could consider, right? And so then I search the data and I try to find everything that looks similar, right? What's the closest thing? So if I have 3 bedrooms, okay, that's good. If I have 2 bathrooms, that's good. If I have a view of the lake, that's what I want, right? And it's an apartment, right? And so we find all these values that are the closest to the values that we're interested in. And then we're able to either classify or predict depending on what our outcome is. Okay. But one thing that I wanted to say was, one thing, I've got so many more things to say. One thing that's really gonna bungle things is, what if you have things like, okay, variable 1 that you're interested in, or predictor 1, is the number of bedrooms, right? Number of bedrooms, it's on a scale from, 1 bed, or I guess technically 0 bedrooms for a studio, up to, and if I'm looking at apartments, maybe 5 bedrooms. That's crazy, right? But it's on a small scale, right? What if I let variable 2 be the square footage, right? Square feet is going to be quite large, right? So now I'm adding a small, so this distance is going to be small, right? And then this distance is going to be huge. And what happens is it overpowers the distance, right? Because we have this huge distance, right? If I compare 1,500 square feet to 2,000 square feet, that difference is 500, which then I square. And then the distance in the bedrooms and the bathrooms, it doesn't really matter. So to avoid that overpowering, we have to standardize all these values first, right? And so let me change my pen back there. When finding the Euclidean distance, Euclidean distance, the scale of the predictors makes a huge, I don't want to say difference again, but I'm going to have to. When finding the Euclidean distance, I'll think of a better name. When finding the Euclidean distance, the scale of the predictors can greatly affect the distance, right? Can greatly affect the distance, right? And so what I want to do is I'm just going to steal this this formula here, and I don't want to write it out again, right? I'm going to delete that there. So if x1 or if predictor 1 is number of bedrooms, right? And if predictor 2 is the square footage, right? The scale of the number of bedrooms, the scale is maybe from 0 to 5 at most, right? Whereas the scale for the square footage is maybe, I don't know, 500 to, let's say, 3,000, right? And so what happens if we're trying to minimize this distance, really what happens is it ends up focusing on this huge one, right? And so exactly, so it's not robust to these values. So nice, right? And so it's kind of being swayed towards, okay, then I'm going to do everything I can to get my predictors to be as close in square footage, and forget about the number of bedrooms, forget about the lake view, forget about everything else, and just focus on that square footage, right? And so then when we try to minimize the distance, right, we end up focusing on the values on a huge scale, right? So then we end up only considering the square foot, right? Because it's on a huge scale. Because it is on a large scale, right? So what we do and what we have to do to avoid that is we standardize all these values. Now, we've standardized things before. It means calculating a Z-score, right? And so, and again, there are many ways that we could standardize things, okay? But for us, we're just going to focus on one of these, right? So when we're just beginning, we only need one method, right? It might not be, you know, the best method for what we're doing, but we need somewhere where we can start, right? And so this is kind of a starter pack, right? And so the main way that we standardize these scores is through Z-scores, right? And so to avoid this, we need to standardize all the predictors. We need to standardize the predictors, right? And to standardize, what we're saying is we need to calculate Z-scores for each of the predictors, right? And for each of the observations. So calculate Z-scores for all the observations of all predictors, or at least the ones that you are interested in, right? But typically it's all done in the background, right? But you want to make sure that it has been done, right? And so you want to standardize all these predictors. And usually we find that the Z score, oops, Z, remember, is X minus X bar over S. Or maybe not remember because we didn't use it this way, but this is a fact, okay? And so X minus X bar over S. And so what we're saying is we take the distance X is from the mean, right? And how many standard deviations is the distance? Number of standard deviations is how we find that distance, right? And so, right, what that means is if you have an observation that's close to the mean, then you get a Z score that's close to 0, right? X minus X bar. And then as we increase, right, our Z scores, then we're moving further and further away from the mean. Right. So now we can work freely and we can compare, okay, the standardized value for the number of bedrooms, right? Well, that's going to be how far from the mean number of bedrooms, taking into account the spread of the number of bedrooms, right? And so once we have these standardized values, then we can go ahead and they all behave the same way, right? So there's not one that's overpowering our distance metric. Okay. So one thing that's different about categorical data, especially, right, or categorical predictors, is when we were running regression or regressions with categorical predictors, then we used one of those categories as a reference variable, right? So it was the jumping off point, okay? And then we adjusted everything based off of that. We're not going to do that anymore because now we're trying to classify things, right? So we're not really building models anymore like we were, right? Linear models, for example. Now we're just trying to incorporate all the information that our data gives us. So now we use the one-hot encoders, right, which has all of the zeros and ones. So all of the categories are used and one hasn't been taken out as a reference. Okay, so for K nearest neighbors, right, and other machine learning things, because we're trying to use the data to guide us, right? And so we don't want to remove one now anymore like we did with the predictors. Why did we remove it? Because we were concerned about multicollinearity, right? I only need to know 4 out of 5 outcomes. And if all of those are off, then it has to be the last one, right? So that's how we used it for regression. But now we've got, we need to use all the data. So for K nearest neighbors, categorical variables are recoded, that's the word I'm looking for, are recoded as one-hot encoders, which really means, and we've heard that term before, but we just kind of mentioned it and we said, okay, we're not going to do that yet. But the one-hot encoders is when each category is recorded or is recoded, maybe I'll say, is recoded as a binary variable. Unlike regression, right, all the categories are kept. So unlike regression, all the categories are kept. Right? In regression, we ditched one and we said, okay, now I have these dummy variables, and so they behave a little bit differently. Right? Because when I was doing regression, we didn't want to have that redundant information of, well, yeah, if all of them are off, then I know it's this one, right? Whereas here, we want to keep all this information and we just want to look at our sample and compare it to the values that we're interested in. Right? Slightly different. Okay, so we've standardized our data. And if we have categorical variables, then we've spread them out as one hot encoders. And so now we have these series of binary data. And then now we parking lotted and we said, okay, well, the K is the number of neighbors that I consider, right? And so now let's talk about how things change, right? And so I've got a page break here, so this is going to look crowded, but it's actually not in the end. K is the number of neighbors we will consider. Okay. If K is 1, are the points? Yes. So those points, we don't just have, the number of bedrooms in the sample compared to the value that we're interested in. So that would be the distance. So we're going to have some, and maybe I should clarify that here actually, right? X is, let's say, our data points, right? So what we have in our data. And U is going to be the value that we want to use as a predictor, right? So that predictor value. Where can I put this here? So here, let X be the data or the sample information or observation 1, and U be the predictor value. Predictor value of interest. Right? How far is this sample? I guess observation is better than information. Sorry, I had to get there. Sample observation. So the observation and then predictor 1 or feature 1 might be the number of bedrooms. Feature 2 might be the square footage. Yeah. So X is going to have that sample information, and then I see how far is it from that predictor value that I want that I'm interested in. And then the closer that they are, right? And then we square it to amplify that distance and also to make it positive, right? We can't take the square root of a negative number. So we square it. And then for the value, so the total observation where this distance is minimized, that's your nearest neighbor, right? It gets confusing because we're talking about multiple predictors, right? And multiple features. So yeah, so A and B are the features, right? Or A here would be, I can see why, right? It is confusing stuff, but A here would be your sample information and B would be the predictor that you're interested in. How far is it from the sample? Nice, good. Okay. So K is the number of neighbors that we're going to consider. So for example, right? If I let K be 1, then it's just going to be whatever the nearest neighbor is, right? So then I only look at the nearest neighbor. Whereas K could be the sample size, right? And so here we could go to as large as K equals N. Why wouldn't we do that? We wouldn't do that, right? If I let, or I guess N minus 1, no, it could be N, sorry. Why would that be bad? Well, then because everyone gets the same classification or the same prediction, because then you're looking at the entire sample size, right? And so all observations or all predictors, all predictions / classifications are the same. If we consider the entire sample size every time. If we consider the sample size nearest neighbors. So we want to find a balance here. So if you're only looking at the nearest neighbor, then you're not really going to be finding a lot. That's something that you could do, right? But usually you want to find a little bit of a trade-off, right? Because you want to have kind of average outcomes, right? Or average classifications, I guess. So here we want to find a K, right? That gives us this kind of balance, right? Where we're not just looking at the nearest neighbor, but we're also not looking at too many of the neighbors, right? Because then we lose a lot of that nitty gritty kind of information, right? And so we want to find a K, or we want to use a K. Use a K that captures kind of distinguishing information. That captures distinguishing information. Right, so we want to look at maybe K equals 3, K equals 4, and we want to look at and compare the two. Okay. So usually we consider kind of K equals 3 or K equals 4, but it depends. Oh, so the neighbors are determined by that distance metric that we were just talking about. So the Euclidean distance is going to tell us what the neighbors are. Right? And so now we can classify as everyone as, okay, you're my closest neighbor, you're my next closest neighbor, you're my next closest neighbor. So then we would just look at, okay, if I want K equals 3, so 3 nearest neighbors, I would find my 3 nearest neighbors. And then I would either take the majority for the classification or the average for the prediction. I think that. Okay, and so so that's kind of nice. Okay, and so K nearest neighbors recap. Okay, we have some set of predictor values. So given a set of predictor values, we use the distance metric. We use the Euclidean distance to find, to rank our neighbors. Okay, so given a set of predictor values, we use the Euclidean distance, right? Let's just focus on kind of the defaults here. We use the Euclidean distance to rank each observation as a neighbor. Okay. And then, right, depending on K, so if K is 3, for example, then we would consider the 3 nearest neighbors. Then if K equals 3, for example, consider the 3 closest neighbors right? And take the majority and the classification, and the classification will be the majority classification. Majority classification of the 3 neighbors, 3 closest neighbors. Or the prediction will be the average of the 3 closest neighbors. Will be the average and I want to say the majority classification of the 3 closest neighbors, so their outcomes, right? But I'll clarify here, or the prediction will be the average outcome for the 3 closest neighbors. Okay. Very confusing, but once you kind of get the rhythm, right, is then we get there, right? So we can extend this and use the prediction as a feature and use the resulting prediction as a feature, right? So as a new feature, and that's where we get that feature engine that we talked about in the beginning, right? So now we're building more features. So we can extend this and use the resulting prediction as a feature in a model, right? In classification or prediction model. I'm not entirely sure if you could use K nearest neighbors again, because then one of the neighbors that or one of the predictions that you're interested in is the nearest neighbor. And so it doesn't really make sense. So I feel that you should be using some other type of classification method or prediction method, okay? So then you could have, for example, y hat is beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and x3 might be the KNN classification or or prediction, depending on, you know, what you're talking about. Right, so you could apply it to a linear model, right? And then, so that's if you are predicting. Okay. And, okay. I don't really have time to talk about tree models, so I think I'm going to parking lot that for next day. But tree models are pretty fun, just because they're so easy to explain. Again, you've got this role where you're explaining your kind of your decisions that you've made, right, with your data. You have to explain it to other people who haven't worked with the data. So then decision trees and trees in general are kind of a nice way to do that. Okay, but we'll save that and we'll talk about trees next day. So we'll leave it at that. If you have any questions, let me know. Otherwise, I'll see you on Thursday. Stop this recording here.